Dear students, let us continue our discussion on sampling and reconstruction. I am sharing the screen here. In the previous video lecture, we have discussed about sampling and reconstruction process. Sampling, as we have seen, is obtaining the continuous time signal to discrete sequence. So this is nothing but analog to digital conversion. Okay, while the reconstruction process enables us to get the continuous time signal back from the discrete sequence, and this is digital to analog conversion. This can be considered as digital to analog conversion. Okay, this is feasible under some constraints, like the signal has to be band limited, time domain signal has to be band limited, and sampling frequency has to be higher than twice the maximum frequency in the signal. And the reconstruction filter has to be ideal. However, under practical limitations, we can approximately get the original signal back. So to illustrate this better, we have seen the time domain signal and the process of sampling in time domain, and the process of a frequency domain spectrum, and process of like the sampling and reconstruction in frequency domain. However, please note that this time domain signal and this frequency domain spectrum are not exactly corresponding. So in a way, writing this strictly as time domain to frequency domain is not correct. Okay, but this is like approximate. So I will probably write here. Okay, so approximate in the sense that actually if you have some other spectrum which is sync square, then you will get this. Okay, this is just a analogy I am trying to bring, but not the exact correspondence here. Okay, and we have also discussed to change the sampling rate. There are two ways. One is time domain to bring back the discrete sequence to continuous time and change the sampling rate. Sample at different sampling rate, or directly changing the sampling rate in discrete domain. On this, we will have a better discussion or a further discussion of conversion of sampling rate in subsequent video lecture. In this video lecture, let us concentrate more on what will happen to the spectrum when I sample. In the previous discussion, we have seen when conversion from xc of t to x of n. So what we discussed specifically is, if we have x of t, x c of t, from there we first sampling process, we get xs of t. Okay, from xs of t we get x of n, and finally xc of nt is x of n. That is the samples we obtain here are from the continuous time signal. Okay, this is in time domain. Fine, at regular intervals. So we would like to see in frequency domain what is its implication. That is, what is the relation between x of e power j omega, okay, that is x of n Fourier transform, discrete time Fourier transform, and Fourier transform of xc of t. Okay, so we would like to establish the relation, similar relation, even in the frequency domain. We will also try to see with some of the examples how does this the spectrums will look like in discrete Fourier transform domain. Okay, so these are the time domain relationships we have seen in the last class. Okay, so these are the time domain relationships. Okay, during sampling. In sampling, let us write. Okay, here objective is to establish in frequency domain, both mathematically as well as pictorially, how does the spectrum of x of n is related to the spectrum of xc of t, or x of e power j omega. Okay, so let us now start the discussion. So xc of t be the time domain signal initially we have with us, and then xc of j omega is its corresponding continuous time Fourier transform spectrum. Okay, this is continuous time Fourier transform. Okay, of of xc of t. Now, we have seen in the previous relations that xc of t, xs of t is obtained as the multiplication of xc of t with impulse train. Okay, that is written conveniently like this. So xs of t is multiplication of xc of t and impulse train. Okay, the whole rest is impulse train. Fine. So when I multiply, I can rewrite xc of t as xc of nt because it's non-zero only at those locations. Fine. Then this is one time domain expression for xs of t. However, we have seen this relation in frequency domain. If we would like to obtain xs of j omega, it is the convolution of xc of t or xc of j omega, Fourier transform of xc of t or xc of j omega, and impulse train. That is obtained by this. So the first relation is obtained by multiplication of xc of t and impulse train. Okay, and this is obtained by convolution of xc of j omega and impulse train in frequency domain. Fourier transform of impulse train. Okay, impulse train in frequency domain or Fourier transform of impulse and Fourier transform of impulse train. Fourier transform of impulse train. Okay, this we have seen in the last classes. Okay, so I'm just bringing the necessary relations to accomplish a final task of relating x of e power j omega to xc of j omega. Okay, so what is my objective now? So now let us understand that the Fourier transform of this x of j omega, xs of j omega, can also be obtained from this expression. Okay, so from 2, okay, let us write from 2, I can take the Fourier transform to get x of ss of j omega. This is from 2, right? And this you can see when I take Fourier transform here. From 2. Okay, so when I take Fourier transform here, what will happen? So this term is, see, Fourier transform is applied with this is what kind of Fourier transform now should we take? This is a continuous time signal, and hence the continuous time Fourier transform will come. That is integral e power minus j omega t dt. Okay, and the signal xs of t is written here. Now you can see that only this term is dependent upon small t, and hence remaining terms can be out, and this term integral over this is a delta function. So the integral over delta function enables us to replace the small t by capital N-T. That is non-zero only at small t equal to capital N-T, and hence I can write like this. Okay, so and this is xs of e power j omega, right? Now on parallel lines, see, if I directly want to find Fourier transform of x of n, here it is a discrete sequence, and hence I will try to write discrete time Fourier transform. Okay, so and then I can write it as x of n e power minus j omega, as I have written here. Now you can see that by comparing 3 and 4, you can see that x of n is exactly same as xc of nt. That is, the sample signal is written as sequence, normalizing with respect to time, right? Capital T, time period. At each 0 location and time period t, time period 2t, I have 1 samples. I am denoting as 0, 1, 2, 4, and so on. 1, 2, 3, 4, and minus 1, minus 2. Okay, so here these are corresponding time domain sequence from corresponding continuous time sequence, and these are exactly the same magnitude samples. So these are same. So then while comparing these two, what do we see is that, so this omega t, omega into t is equal to small omega. So since xs of j omega, this is the like the difference between xs of t and the x of n is normalization with respect to capital T. Similarly, here you can see that this small omega equal to capital omega into t. So we are multiplying with respect to capital T time period with the continuous time frequency domain to get the discrete time domain. Okay, so here it is dividing the axis by capital T to get the sequence indexes. Here it is multiplying the omega axis with capital T to get the small omega axis. Okay, and further we can see little more things. We will just a little after. Meanwhile, let us establish our final task, that is relating the Fourier transform of xc of j omega or x of t, xc of t, Fourier transform of xc of t and x of n. So how do we do it now? So now let us yeah. So as we have seen before, x small omega equal to capital omega t to t, and thus we have a axis transformation given by this for transforming the continuous time Fourier transform to discrete time Fourier transform. Okay, now right, and xs of j omega as we have seen here is this from equation 1. Now using this transformation of the axis or the Fourier axis, Fourier frequency, then we can write x of e power j omega as xc of j omega by t minus this, right? So you can see omega s is nothing but 2 pi by capital T, right? And hence we can write x of e power j omega is equal to xc of j omega by t minus 2 pi k by t. That is, this axis of xc of j omega is normalized by capital T, and this spectrum in time domain of the continuous time signal repeats at interval of 2 pi by capital T, right? It repeats at each interval of 2 pi by capital T. This is referred to as omega s. So the consequence of sampling, that is converting from xc of t to x of n, is twofold. One fold is the repetition of the spectrum at regular intervals of 2 pi by capital T. Other aspect is normalization of the axis by capital T. Okay, fine. Let us see with an example on these aspects. Okay, I'm sharing it again. I think sharing is off. Right. So as we have seen, the transformation of x of n or sampling process enforces two changes, that is repetition at 2 pi by capital T and then the normalization by capital T. So let us see. So now let us assume that, let us directly look at in frequency domain now. So let this be x of j omega or xc of j omega. Okay, and say for example we take from minus 500 to 500. Okay, h is omega by 2 pi axis. Let this be. Okay, now assume that this is the Fourier transform any way of, so it's Fourier transform of xc of t. Okay, now what we wish to do is we would like to sample this. So this is x of xs of t. So if we sample it, we would like to sketch the spectrum here. How does the spectrum look like? Where does it repeat? This spectrum, because of sampling, okay, that is multiplication with the impulse train, there will be convolution and repetition of the spectrum in the frequency domain. Where does it repeat? It repeats at every omega s. See, let omega s in this example, omega s is equal to, okay, 200, 2000 into 2 pi. Okay, that is, let this be omega s. Then where does it repeat? This be omega axis, and hence this is 500 into 2 pi. So for everything into 2 pi, assume that. Okay, I'm not writing 2 pi everywhere. 2 pi, and this is, the location is 2000. Okay, and hence this is 1500. Okay, and then this is minus 500, and this is minus 1500. And this is minus 2000. Okay, right. So now this is what is that I have sketched here? Xs of j omega. The spectrum of, again, this is the frequency domain representation. Oh, fine, good. Okay, of this Xs of t. Now, what we wish to do is, we would like to represent in x of e power j omega. That is, see from here, Xs of t, what do we do for getting Xs of t to x of n? If you wish to get, what do we do? There is a normalization by capital T. Okay, so that means you divide the frequency axis, this time axis, by capital T to get the sequence alone without having the time period information there, right? In frequency domain, what we have seen is small omega is equal to capital omega into capital T, right? There you divide the axis by capital T, here you multiply the axis by capital T. See, this 200 can also be written as, okay, so 2 pi by capital T. Why is this? Because, so 200 into 2 pi, okay. Why is this? Because, see here, this is sampling frequency, here is 2000, and then the time period is 1 by 2000. Okay, that is given. Assume that for us. Assume it is given. Okay, and with that we have sketched this. Okay, so that's why this is like this, right? And so since anyway we are writing 1 by t. So omega s I will write, rather than writing here, omega s is equal to 2 pi by capital T I will write. Okay, right. Okay, so now if we multiply with capital T, what does it happen? So this is minus omega is equal to, I will write with different sketch, minus 2 pi by capital T. Okay, this is 0 axis, this is 2 pi by capital T. Okay, so it repeats at every 2 pi by capital T or 4 pi by capital T and so on. Integer multiples of 2 pi by capital T or omega s, correct? So now in discrete domain, how should be the discrete Fourier transform? So we would like to, how will it be is the question. Would like to sketch it here. Now assume that we keep the same spectrum here. We don't want to change the scale of the spectrum, but we would like to change the axis. Yeah, what should I keep here? This is 0. Okay, and this is what? At what point does it repeat? Now multiplied by capital T, right? So it will repeat at 2 pi, and this will repeat at minus 2. This will minus 2 pi and 4 pi again. Okay, and since this is from minus 500 to 500, Okay, into 2 pi. What is this now becomes? I am capital T equal to 1 by 2000. So this will be minus 1 by 4 or 2 pi by 4 or pi by 2. Okay, and this is pi and this is minus pi, right? And this is 3 pi by 2 and this is minus 3 pi by 2, right? And hence the discrete Fourier transform of this x of n, it looks is given by this x of e power j omega. So what did we plot here is x of e power j omega, right? So please note that there is a 1 by t term here for the magnitude. Okay, this comes from the expression itself. Here also same will be there, 1 by t term. Okay, right. Right. So here if we see there is a 1 by t term. Okay, so that's missing in our expression. Right. Okay. Right. Okay. So everywhere 1 by t term. Fine. Okay. So this is what happens in the discrete time spectrum. Okay, discrete Fourier transform spectrum, discrete time Fourier transform spectrum, right? So you can see that the spectrum of discrete time Fourier transform always ranges from minus pi to pi. Oh, it is periodic with period 2 pi. This is the one cycle of the spectrum. Okay, and if you like to extract this information of the signal, if there is no aliasing, you can completely get the information of the signal from minus pi to pi region. Okay, so and periodic with period 2 pi, which is nature of x of e power j omega. Right? Okay. Oh, so hope this discussion is clear. You can you are suggested to work out with few more examples to get the clarity on the same. Thank you.